This week's focus is on the math skills that are associated with this particular unit. And the first thing we'll address are those free body diagrams, net forces. We'll do a few more of those, and we'll look at how those net forces can be used to predict the future motion of an object. First, you'll be given a free body diagram, all the arrows on it, all the labels on it. And in that free body diagram, I'll tell you which direction the object's moving. What you'll have to do is find the net force. You'll have to figure out what the net force is going to be so you can compare it to the motion of the object to make your predictions, to figure out what's going to happen to that object. Now, in some cases, I will specifically ask you for the net force. And when I do that, when the question says, what is the net force? You need to give me the magnitude and direction of that net force. The magnitude is the Newton number, like 18 newtons. And the direction part will be the angle at 127 degrees, at 40 degrees north of west. That's the direction part. You only have to do that when I ask you what is the net force. If all I'm asking you to do is to predict the future motion of the object, what's going to happen to the motion of the object, and I don't ask you for the net force, then you don't have to go quite as far. If I'm just asking you to predict the future motion, you have to get as far as drawing the triangle at the end, taking your vertical component and your horizontal component and looking at what the hypotenuse looks like, and then just based on the shape of that hypotenuse, you should be able to make some kind of prediction about what's going to happen to your object. So again, if a question asks you for net force, that's when you got to go all the way. That's the long, drawn-out problem where you actually have to come up with a final answer, a number of newtons, and an angle at which it's being exerted. If it only asks you to make the prediction of future motion, you only have to get to the point where you know which direction the net force is going in. Then you can compare it to the initial motion of the object to decide what's going on. I'm going to show you an example of both. Now, to figure out the future motion of the object, it's all about Newton's first and second law. They are basically one and the same. The first law and the second law are both really about acceleration. The first law tells us what happens when there's no force, how an object will accelerate when there is no net force. The second law tells us how it will accelerate when there is a net force. First law says if there's no net force, an object will continue doing whatever it's doing. In other words, if there's no net force, there will be no acceleration. That's a good way to think about this law. First law, if there's no net force, there is no acceleration. So if it's not moving, if it's stationary, it will remain stationary. If it is moving, it'll move in a straight line at a constant speed. Both of these scenarios imply that there is no acceleration, because if there is no net force, there is no acceleration. Second law tells us if there is a net force, it'll accelerate in the direction of that net force. So first law, if there's no net force, there's no acceleration. Second law, if there is a net force, there is acceleration. And again, accelerating in the direction of that net force. Now, that part is all about comparing the direction of the net force to the direction of motion. If the net force is in the same direction as motion, the object will speed up. If the net force is in the opposite direction of motion, the object will slow down. If the net force is in the same direction as the motion, the object is moving to the right, the net force is to the right, it will speed up. If the net force is in the opposite direction of motion, it will slow down. So if the net force is to the right, but the motion is to the left, it will slow down. So again, object moving to the right, net force is to the right, speeds up. Object moving to the right, net force is to the left, slow down. If it's at any other angle, it will change the direction of the object. So if our object is moving to the right and the net force is up, the object will turn upwards. It would move at a constant speed, but it would turn upward. If it's angled it'll do two things at the same time. So if it's moving to the right, but the net force is down and to the left, because part of that is to the left, this object would slow down. Because part of it is down, it would turn downward. If you have any questions or concerns about that, go back and watch my video on Newton's second law. Now, this is an example of a problem where you do not actually have to figure out what the net force is. And the reason you don't have to figure out the actual net force is because the question is just asking you to predict its future motion. The question is not asking for net force. So this is one of the quicker types of questions to answer. To do this, we have to resolve our horizontal and our vertical components. First, the horizontal. I've got 5 newtons to the right and 1 newton to the left. Two ways I can approach that. Big number minus little number, and the direction will be the same as the big number. Or I can make this positive, make this one negative, add them together, and the sign will tell me the direction. Positive means right, negative means to the left. I'll do it the first way. 5 minus 1 is 4 newtons. And it's going to be to the right in the direction of the larger force. Now I'll resolve the vertical part, up and down. I'll do this one the other way. Up is positive, down is negative. So I'll add those two together. Positive 7 plus negative 4 is positive 3. And the positive tells us that it will be upward. 3. Remember, when you're drawing this, we use the tip to tail method. You attach the tail of your new vector to the tip of the previous one. So our previous vector ended here. That's where I will attach the new one. It's like you just continue going from where you left off. The net force would be the hypotenuse. There to there. Now, we're not even going to figure out what the magnitude or direction of that is. We don't have to do Pythagorean theorem. We don't have to do the angles because it's not asking for that. It's just asking me to predict the future motion. And to do that, I will compare these two arrows. My object is moving to the right, and there is a part of this that goes to the right. So the object will speed up.
Teachers, please excuse this interruption. Would the following students please report to the media center at this time?
This is going to be a long announcement.
Jaden Harris,
To the right.
Hawkins,
Part of this,
Hawkins,
4 newtons of it
John
is
Pettis,
to the right.
Avery Hill,
Same direction as
Haley
speeding
Hill,
up.
Jody Hodge, Isaiah Holston, Sarah Hood, Connor Jackson, Jakira Jacobs.
At the same time, there's an upward
Jalen
component here.
Jefferson, Shemaiah Jefferson,
Object's moving to the right, and there's an upward part.
Aliana Jenkins,
So the object will turn up.
Diamante Jenkins, Deshaun Jenkins, Tania Jenkins, Daquan Johnson, Jordan Jones, Sarah June, Labria King,
So that would be the answer to the question.
Darrell Kirk, Brittany Lee,
Again, I'm not figuring out the magnitude of direction because I wasn't asked for it.
Littner, Riley Bayer, Jacob Marlowe, Alena Martin, and Mariah Martin. Would you please report to the media center at this time? Thank you.
Now this problem is a bit different because it does ask for the net force and the prediction about the object's future motion. So this is the one where you have to go all the way. This is the one where you have to calculate everything. And I chose this one intentionally because this is the type of problem that most of you are still struggling with. You haven't done enough of these to figure out how to do it yet. So I'm going to do another one here as an example, and there are a few of them that you'll have to do on your practice sheet today. Whenever you're faced with a situation like this where you have this angled vector at the top, your first job is to break that down into its x and y components. We start by drawing that vector. There's a 10 Newton force up and to the right. I then have to break this down into its x and y components. So I'm going over and up, and that's what I draw. I went over and up. That 90-degree angle should be opposite of that hypotenuse, and again, you need to connect your vectors tip to tail. I attached the tail of my new vector to the tip of my old one. I went over and then up. This will be my x component, that will be my y component. And again, what I'm going to do is I'm going to break this down into its x and y components so I can take it out of that drawing altogether and replace it with something I can work with. This is where sine and cosine come into play, and you got to know what sines and cosines are all about. This is my 50-degree angle. It's the angle I'll use for both calculations. I'll start with sine because in the little sentence that we use to remember this, sine is first. I have my angle, so I'll put that in there. I know it's already 50 degrees, so I'll say sine of 50 is equal to the opposite over the hypotenuse. Sine is opposite over hypotenuse, some old hippie. Sine is opposite over hypotenuse. Opposite is the side of the triangle that is not part of your angle, so that's y. The hypotenuse is 10. Sine of 50 equals y over 10. Sine of 50 is 0.7660. Again, that is equal to y over 10. Multiply both sides by 10. My y component is equal to 7.7. Rounded. That's how I find the y. And again, it's y because we use sine, and sine is opposite over hypotenuse. Cosine of 50 is going to be equal to adjacent over hypotenuse. Adjacent is the side that's actually part of your angle. So my x and my hypotenuse is still 10. Cosine 50 is 0.6428. That is equal to x over 10. Multiply both sides by 10. My x is 6.4. Once you do have one, you could use Pythagorean theorem to figure out the other. That would be perfectly valid as well, but you do need to do either sine or cosine to get one of those other sides. And I have noticed a lot of you have been making mistakes with that, so it might not be the best way to go. If you do use Pythagorean theorem, you've got to understand that you have c squared. You already have c squared. That's your hypotenuse. That's the 10. So I can say 7.7 squared plus b squared equals 10 squared. Again, I already know c squared. That's my hypotenuse. 7.7 squared is 59.29 plus b squared equals 100. Subtract 59.29 from both sides. I end up with 40.71. Square root both sides. My missing side, x, is 6.4. So get the same answer both ways, but I have noticed, looking at some of your work, that some of you are doing that Pythagorean theorem side wrong. And again, once you figure out a pattern here, it's sine 50 times 10. The other one's cosine 50 times 10. It's so much quicker just to punch that in your calculator than it is to do the whole Pythagorean theorem thing. Again, our goal here, and the whole reason why we did this, was to get rid of this angled vector. We can't use these angled vectors. we need everything to be either in the horizontal or the vertical for us to do our math. So now we've got a y component, an upward one of 7.7, and my x component goes to the right of 6.4. That's the whole reason why we did all that, is to get rid of that angled vector from our question and to give ourselves something that we can actually work with. All right, now that we got that, we can go ahead and simplify our vertical and our horizontal components of this. These two get added together. So over here I have 11.4 to the right. I have 4 newtons to the left, so I'll subtract those, and I'll get 7.4 in the direction of the stronger force. So it's 7.4 to the right. I have 7.7 up and a 3 down. I'll subtract those. 7.7 minus 3 is 4.7. That'll be upward in the direction of the stronger force. That is my hypotenuse. Now, if the question had just asked to predict the future motion, that's where we could stop. And we would see that there's a part that's backwards, so it would slow down. There's a part that's up, so it would turn up. Again, if it asked just to predict future motion, we wouldn't have to do much more than this. But it's beyond that. It's asking us to say what the net force is, so we do have to calculate a number. To get the magnitude, the Newton number, we'll use Pythagorean theorem. A squared plus b squared equals c squared. 7.4 squared plus 4.7 squared equals c squared. 7.4 squared plus 4.7 squared is 76.85. Square root both sides. Our hypotenuse is 8.8. And that's the Newton part of our answer. I still need to figure out the angle part. To do the angle part, now I'm going to find that angle there. Just label it theta. And I can use sine, cosine, or tangent. Doesn't matter what trig function I use. I always go with sine because it's the first one. It's the easiest one to recall. It's opposite of our hypotenuse. So the sine of this angle will be the opposite, which is 4.7, divided by the hypotenuse, which is 8.8. 4.7 divided by 8.8 is 0.5341. Now that's not the angle. To get the angle, I have to take the inverse sine of that. Inverse sine is the second function button, or the shift button, and then the sine key. So second function or shift, sine, that number, 0.5341, tells us we have an angle of about 32 degrees. Now that angle may or may not be the angle that we want for our answer. That depends entirely on the whole unit circle thing, which I know a lot of you struggle with. You've got to remember on a unit circle that you're taking a circle and dividing it up into 4 quadrants, putting a cross in the middle of it. Over here on the right side, east is 0 or 360, either one. 0 if you're just starting, 360 if you're finishing. North would be 90, west would be 180, and south would be 270, adding 90 degrees each time because each of these black lines is a 90-degree angle. The angle that we would use for our answer depends entirely on what angle we have and what quadrant we're in. So for the green one, if I had an angle of 36, pretty close to what we've calculated here in this problem, I could just go with that. This would just be 36 degrees because it is telling us how far from zero we are. We are 36 degrees from zero. If you are in this first quadrant and you know the angle on the bottom, that's your answer. And you don't have to do any further calculation. You don't have to do any further work. If you had this angle up here, then what you would have to do is subtract it from 90 to get your angle down here. So if I knew this one was 50 degrees, I do 90 minus 50. I know that angle down there is 40, and that's the one I go with. Always trying to say how far from zero we are. Take a look at this one over here, 50. That's not going to be the angle we want to use in the unit circle. So we have to figure out how far away from zero we are. Well, this is 180, and I am 50 degrees short of it. So I do 180 minus 50, and I measure this angle here, which would be 130 degrees. And again, it's just reasoning and thinking your way through. If this one is 180 degrees, and I am 50 degrees short of it, that means I must be at the 130 degree mark. I must be 130 degrees away from zero. Let's take a look at this orange one down here. 55 degrees. And 55 degrees is not necessarily the angle we want to work with, because 55 degrees is really over here somewhere. We have to indicate what that is. And again, we reason our way through. That's 180. I've gone 55 degrees past 180. So I do 180 plus 55. And my angle is 235 degrees. From here all the way back around to zero is what I'm measuring. And that is 235 degrees. I am 235 degrees away from zero. Again, it's just thinking your way through it. That was 180. I want 55 more. Atom. Finally, if I land over here somewhere, I'm 10 degrees away from 360. I'm 10 degrees short of 360. So I do 360 minus 10, and this whole angle here, all the way around there, would be 350 degrees. That's how it works. That's how the unit circle works. You're trying to figure out how far away from zero you are. So let's go back to this question. Unit circle. Zero's there, 90's there, 180 and 270. Just adding 90 every time in case you forget what those numbers are. My vector is here going like this. And we really just draw this arrow the same as we would draw that arrow, going that way. Put the tail of it on the intersect there in the center. This angle is 32. When we look at that, we are 32 degrees away from zero. So that really is the angle that we want to use. And this unit circle stuff is pretty significant and pretty important. We're going to be doing circular motion at some point. And circular motion, you better know your unit circle. You better know your degrees. So there you go. That's the net force part. Now we got to predict the motion of the object. We got to figure out what it's going to be doing in its future. And for that, we look over here and compare its motion with our vector. It's moving to the left. Our vector has a component to the right in the opposite direction. This object will slow down. Get motion to the left. There's a certain component that goes up, 4.7, so it will turn upwards. have it. That's how one of these works. I've given you several to try. You got to work through them. You got to wrap your head around how all this works.